Section 5.3, we are going to do the divergence and the integral test. First, what is the divergence test? The divergence test goes like this, okay? That is, if for a series such that looks like a regular series, okay, that goes to infinity, an, and goes from 1 to infinity, for this series to converge, we have to have an, each an has to go to 0. If it doesn't go to 0, you got nothing. Now, why is that? The proof actually is quite straightforward. What happens is that you calculate what is the limit of this thing. Let's say it does converge, okay? If it converge, that means, that means if the limit of, let's say ak, okay, as k equal to infinity, is equal to the limit of ak is just the difference of two partial sums. So we'll write that out. Limit of k goes to infinity, sk minus sk minus k plus 1. K minus 1 or k plus 1? Not that it matters, just yeah, you see, ak is the one left, right? If you subtract the rest of the sum. And then that, by definition, if this exists, that means s of k will go to the limit, right? And so does sk minus 1. So that equal to 0. See? There's just a quick, simple trick to prove that ak has to go to, and for the limit, if the limit exists, then the ak has to go to 0. Now, of course, the opposite isn't necessarily true. Just because your terms go to 0 themselves doesn't mean they will add up to become 0. The harmonic series is the most obvious example. So that's the divergence test, is if the limit, well, actually, for a series, that's not the divergence test. The divergence test is saying it the other way. That is, if the limit is not 0, then if the limit of each individual term is not 0, of each an is not 0, as n goes to infinity, it equals to the constant, or you simply can't, it doesn't exist. Okay, if in that case, then the series has to diverge, because for convergence to happen, this naturally will be a consequence. So the other way of saying it is, if the limit doesn't exist, then it will diverge of each term of the individual terms. If the limit doesn't exist or doesn't go to 0, well, basically, if the limit of the an doesn't go to 0, then it's not gonna converge. It will diverge. All right. So now let's look at example 5.13, which is a quick and easy use of the divergence test. So please do that as part of your homework. Next, let's consider something called the integral test on page 472. Now, the integral test is, to discuss it, let's first investigate the harmonic series again. So the harmonic series is this thing goes from n equal to 1 to infinity, but right now we'll just consider up to k, the partial sum sk, which is adding it up to k, which is, of course, 1 over 1, okay, plus 1 over 2, and so on, going all the way to 1 over k. And then we're also going to consider the integral, which is this thing right here, from 1 to k of 1 over x dx. Now, the relationship of these two things will we can draw it in a graph to come out if we consider this thing as area under the curve. So let's draw this graph here, which is something like that. Here is 1, okay? Here's 1. And then, and the way we want to draw this graph is, look at the next page. Okay, so we're going to draw it like this. So this is 1, and then this point is the next one, okay? That's 2, and that's 3, etc. and 4, and so on. Now, as you can see, then this is 1, the distance here is 1, so the area down here is the first term, right? And then the second rectangle, the area down here is the height here is is 1 over x, right? This is the y equal to 1 over x graph. So the height here is 1/2. So that is 1/2 times 1, and so on. So the rectangles we're drawing right here, all the way down to k, okay, 4, and then all the way down to k. Here's k here. So each area of this rectangle that I'm drawing, it will stick out above the graph of 1 over x, which means that this sum is bigger than integrating from 1 to k. See, because when you integrate from 1 to k, you're only going from this line, right, all the way to this line. So all these things are sticking out, right? So then is bigger. And as a result, if we say this sum is bigger than that, and then the next thing we're going to say is we're going to calculate the integral. The integral, of course, equals to natural log of k minus natural log of 1, which is just 0. Okay, this is 0. And therefore, this integral equals to natural log of k. And as we allow k to go to infinity, a natural log also goes to infinity, which means that this sum is bigger than something that goes to infinity, which means the harmonic series diverges. We have already proven that. This is yet another way of proving it. See? Very neat. But what the difference here is that we're comparing this to an integral. Okay, and this will build the foundation of our integral test. Next thing we need to look at is something similar, but this time we're going to do a different sum. Okay, that's similar to the harmonic series, but we'll have n squared. Now by the p series, sorry, we haven't talked about the p series yet. Never mind. Now this is going from n equals to 1 to infinity, but it looks very similar to the harmonic series. But we are going to do this thing in like this. Where's the graph? All right. We're going to draw a similar graph, but first we'll write it out. What is this thing? This is, of course, 1 over 1 squared plus 1 over 2 squared, and so on. You go all the way to something. But first, we are only going to consider it up to k, okay, for now. We're thinking about the infinity case, but for now, let's stop at k. So we'll add it all the way up to k, the same as the previous case. And similarly, as this previous case, we're going to consider the integral of this integral right here from, what was it, 1 to k, all right, 1 to k, and sure. Anyway, 1 to k of 1 over x squared. As you can see, the x squared corresponds to the n squared. I just changed the variable. Now, what does this graph look like? Now, this graph is, we will start at, the graph is y equal to 1 over x squared. All right, so, so at 1 is, here's 1, and we're going to draw this differently. Okay, this is 1, and then this is, but we're going to draw it backwards. This is 1, okay, and this is 2, and so on, and 3, all the way up to k, but we're going to draw everything to this side. In other words, we're going to do the right, this is the left-hand side, and this, we're going to do the right-hand side, and then draw all the way up to k. This is k right here. And then when you examine the graph, then you realize that that it equals to, this thing is bigger than that, but only if we integrate from 1 to k. We're still missing this 1. See, there's a 1 times 1. My graph is not that proportional. So it's 1. This is also, this value is also 1. Okay, so then this area is 1. So the graph, so y equal to 1 over x squared is bigger than all the rest except for this part. Okay, we need to add this to it. So if we add 1 to it, then this graph is going to be less than, right? Yeah. See, this thing is less than, if you add 1 to it and all the rest, then it will be the other graph is the area under the curve is more. All right, so that is that's looking pretty good. And then the next thing we're going to notice is that what is the integral of 1 over x squared? We know that that is integrable, sure. But anyway, so we integrate it and apply the power rule and all that stuff. And what is it anyway? Give me a second here. So the integration, when we're done, it equals to 2 minus 1 over k. See, a quick simple integral. And then once we get here, we notice that if we let k become very large, go to infinity, then this will just go to 2, which means that this value is going to converge. If this value converges, that means this value is bounded, and therefore this is a convergent series. That's another way of proving. I don't remember we did it before, but we have done it now. So see that the series 1 over n squared is a convergent series. And because it's increasing and bounded by 2. So therefore, with these two examples, we can, let's see. So in conclusion, what we notice is that the infinite series is bigger than its function. If you convert n into x, okay, the corresponding function from 1 to k, but smaller than that function at some necessary constant. In other words, the infinite series goes hand in hand with those integrals. They're not exactly the same, but they are somewhat close, right? So then as a result, we have theorem 5.9, which states that if you have an infinite series with various necessary conditions, an's are positive, and there's a function f such that f is continuous, decreasing, and f of n equals to a of an for all integers on the tail end. It doesn't have the equal in the beginning because we don't care about the series first finite number of terms. But if after some point fn equals to an for the entire tail end of the series, then the convergence of the integral and the infinite series goes hand in hand. They both converge or they both diverge. All right. Now, what it doesn't mean, well, the integrals are not and Nina mentioned that. I mean, it goes without saying that the integral doesn't exactly equal to the sum. Okay, I mean, as you can see, there's parts missing, but they're more or less the same. That is, they're somewhat close. See, and like of course in this one they're more, but whether they're more or they're less, they sort of stick together. They're pretty good. So it's into the point that they both converge and they both diverge. And but that is not all. Well, but before we say any more about it, please do the example 5.14, which is a direct application of the integral test and is very straightforward. So please do 5.14 as your homework. Next, let's go to page 477 and look at the p-series. The p-series is a sum of a bunch of n's to the power p, and you add that up. Now that looks pretty simple, and most of the time it is. The p-series will get pretty convenient in our future attempts at determining whether a series is convergent or divergent. But first, of course, we need to figure out, well, does the p-series is self-convergent? That depends on whether the p-series, what the value of p is. Now the p, we already know that when p equals to 1, it becomes the harmonic series and it diverges. When p is 2 is that thing which does converge. We already said that. Now, but what happens the rest of the time? If p isn't 1, then let's see. What we're going to do is use the integral test that we just did. And then, let me see. Now first, we don't have to worry about when p is less than 0, because if p is less than 0, so it's negative, then it flips up to be a positive number. And n to some positive power is going to go to infinity, right? So then we don't care. and then it diverges for sure. So what we're concerned with right now is what happens when p is bigger than 0 but doesn't equal to 1. Okay, in that case, we will apply the integral test we just did and consider the integral of 1 over x to the power p, where dx, where p is bigger than 0 and plus it doesn't equal to 1. In that case, we can integrate this thing, okay? And by the time we integrate it and then calculate the details, it equals to, well, we examine the details, that it end up being, well, should I mention the details? I guess. We'll integrate this thing, which is, we will raise the by p, so it raised by the power by 1, okay? So it becomes 1 minus p, divide by the power, 1 minus p, and then we calculate it from, what is the integral doing? From 1 to, 1 to infinity, because we're doing this one. So we do it 1 to infinity, so that equals to, so x start at 1, which is fine. X goes to infinity. That depends on, now remember, p is bigger than 0 and not equal to 1. So that means that we have to consider conditions. If p is bigger than 1, what happens? When p is bigger than 1, p is bigger than 1, so this power becomes negative, right? It effectively goes to the bottom, and then it will become 1 over p minus 1, which is convergent, okay? And then when p is less than 1 but bigger than 0, then this becomes doesn't go to the denominator. This just stays. And then, of course, as x goes in infinity, then it will go to infinity. So if p is bigger than 0 and less than 1, then this goes to infinity. So that is the quick decision. And therefore, that is the result of that too. So for this series, for the p series to converge, we mostly have to remember that for the p series to converge, p has to be bigger than 1. Anything less than that is going to diverge. Basically, yes, it can't even be 1. It has to be strictly bigger than 1. Because being 1 means it turns it into the harmonic series. All right. The next example, example 5.15, is a quick application for the p-series test. So please do that as part of your homework. Next, let's look at the remainder estimate. What that means is, let's say we have a convergent infinite series. How would we calculate the sum? The most direct way of calculating the sum is calculating SK. That is, you add everything up to the k unit. Maybe k is 1,000 or something. So you add it up, and nowadays the Desmos calculator, for example, you can just type in the letter SUM for sum, and then the summation symbol will show up, and you type in 1 infinity and your formula for an, and the output, I mean not infinity, type in k. It's not going to do infinity. And anyway, so from 1 to k, and they'll calculate your SK for you, which is fine. But the question is, how good is our approximation? We know this thing is converging, but if we were to approximate it, how far off are we? Can we control the remainder? And that's what we're going to investigate, is what is the remainder going to be. Now, the remainder by definition is equal, we'll call it Rn, and n is a capital letter, which means it's a fixed number after we've calculated a bunch of sums. Okay, so Rn is defined as the totals 1 to infinity of an minus after you've done the math. Okay, so you calculate, you added it from 1 to n. You have to stop there. You have to stop somewhere, and then what's left is the remainder, and we're going to estimate it. And how are we going to estimate this? We're going to estimate it by using a similar principle as the integral test. So let's look at what it says. Theorem 5.10 on page 478 says, suppose this is a convergent series and we have positive terms. So far we've been working on positive ANs to keep things simple for now. Suppose there's a function that is continuous, decreasing, and f of n equals to an. That is corresponding function f for this thing. Then and then of course we let s of n. Where's our s of n? This is s of n. S of n is the partial sum, right, from 1 to n of this of the series we're talking about, and then we have this relationship right here, which is s of n plus 1. Okay, s of n plus n plus 1 to infinity is less than the sum and less than the the integral is the total summation is defined different in this sense. I mean, it's defined in this sense. It's going to be bigger than the integral. You will add the partial sum, okay, and then calculate the rest of the integration. You integrate the rest of it, and the rest of it is going to be bigger than n plus 1 to infinity, but less than n to infinity. See, that's the only difference between. So it's the value is stuck in between these two things. So that's how you can calculate, or put it another way, is that the remainder that we're talking about is going to be in between the value of integration from n plus 1 on the side, yeah, n plus 1, okay, it's going to be bigger than if you integrate from n plus 1 and less than if you integrate from n. As you can imagine, this integral, as n gets bigger, this integral gets smaller and smaller because it's the tail end of a dying function. A converging dying function, right? So this integral gets smaller and smaller, and that's how we can estimate the remainder. Now, why is this true? What happens is that it's very similar to this principle. It depends on how we draw this thing. Okay, for the first one, we are. So I'm gonna ask you to draw this. Draw this a picture that's very similar to this, and to prove this point. Okay, and the concept is identical to this area, but is more difficult to explain than it really is. Easier if you just draw it yourself. So please prove this. What is this thing? Please prove this theorem. Okay, I mean, at least prove it to your own satisfaction. Prove the theorem 5.10 by drawing the pictures on the following page 480. Okay, the whole thing is done by drawing 480. There's a slight problem though. On page 480, the graph B is labeled wrong. See, the graph B starts at n. Let me show you. See, the graph B starts at n, but that doesn't make it B. This is the one on this side. It starts at n. It should start at n plus 1 because the integral, it says down here, is you're integrating. Let's see. Yeah, you're integrating from the bigger one is integrating from n plus 1. See? So yeah, it's being that you're integrating from n plus 1, right? It should so this part should start at n. It started at n. See? It should start at n plus 1. Then it will make sense. So once you draw that thing, you will demonstrate to yourself why the theorem whatever this is, theorem 5.10 is correct. So please prove theorem 5.10 yourself by drawing those graphs. Now, once you have proved theorem 5.10, which is the remainder theorem or something, then it's a piece of cake. It's a straightforward approach thing to do example 5.16, which is the application of that theorem. Well, you apply it by taking some integration. So that, right. And with that, I think that is about it. That's the end of this section. Yes. So for homework, I have on page 482, I have assigned problems 139, 41, 43, 45, 47, 49, and okay. And then 55, 57, 59, 63, 65, 67, 69, 71, 79, 83, 91, and 92. That sounds like quite a number of problems, but most of these problems are very, very short, so that's not as much homework as it might sound. Yeah, and then when you have finished, I will talk about some of the problems. So please go do your homework. Now that you're done with the homework, let's talk about it. Now first, the sum of a bunch of 2 to the power natural log of n, negative power. Or is it negative or positive? Yeah, it's negative. Okay, now that looks weird until you realize that you're supposed to do a whole bunch of natural log manipulations, that is algebra, and make things look better. And here is how it's done. First, you take the an is that thing, okay? And so you first put the negative sign on top of n, so it becomes 1 over n up here. And then you take the natural log of an, and then that equals to something. And then you get an back by slapping e on it. And remember what e means, and the exponent rules and all that stuff. And finally, you get over here. Okay, the an is just this thing, 1 over n to the power natural log of 2. That's a p series with p equals to natural log of 2. And natural log of 2 is less than 1. Is it? Yeah, because natural log of e is 1, so, and 2 is less than e. E is 2.7 or 8 or something like that. So then, as a result, this series diverges, because p has to be bigger than 1 for the series to converge. So next, let's look at problem 167, which is, I think, similar. Again, you have a weird-looking series, I guess. And what you're going to do is yeah, you're going to rewrite it or something. So you have a weird-looking series. You try to rewrite it, and then it becomes something, and then you even cancel out some of the n or something. Well, 1 to the n. Oh yeah, minus 1. You cancel the n disappeared because you have n to the power, you added the minus 1 at the bottom. So you got rid of the n. So then the question is, what is 2 natural log of n, 2 minus 1? Well, is less than 1 anyway. If it's less than 1, the series diverges. So that's the answer of that. Next, let's look at 169, where you're supposed to calculate the remainder. That is a direct substitution of following the formula. Okay, we'll integrate, in this case, 1 over t from 1,000 to infinity. Crank that out. That end up to be 1 over 1,000. Next, 171, same thing. We'll calculate the integral, which is tangent inverse, blah, blah, blah. That gets you to be tangent pi over 2 minus something, and it end up to be some value, okay? And that is correct. So that's that. Okay, next, let's look at problem 191. Does this thing converge? Well, we're just going to directly apply the integral test, okay? And here's the original. Yeah, don't worry about what I wrote there. There was some attempt I made that failed. So I figure, why don't we just apply the integral test and not worry about any such thing? So here's the original problems series. We'll plug in the function and integrate it, and then we'll let u equal the natural log of x and du and all that stuff, the substitution. And also remember what happens when if we turn x during the substitution, we have to change the endpoints maybe. And once we have done that, we have come up with something like this, which is the same as the p series, right? In fact, what the integral, as you can see, end up being looking like the p series. So the story end up being the same. That is, it converges if p is bigger than 1 in both cases. So that is the answer. The last problem we're going to talk about, 192, is we're supposed to figure out how many terms, how long would it take to add up the harmonic series so that it make it to 100. So So we need the harmonic series. It's just an estimate, okay? So we're going to estimate the harmonic series with the integral. So the harmonic series for 192, harmonic series 1 over n, where we are going to add it from n equal to 1 equal to all the way to a big N, let's say, okay? And we need to know how many terms we need to add up to so that make it so the harmonic series finally crawled its way to 100. And then to do that, we will approximate it with just the integral. It's this is not an exact approximation, but we just want an estimate, so we don't need to be too picky about it. It's close enough for our purposes. So let's do this, and that of course is an easy integration that equals the natural log of n minus natural log of 1, which is just 0. And the estimate is in between whether you start at 1 or start at something else, but we're not going to care about that, okay? So it equals, so the value then it will have to be from 1 to n, and this value has to be about 100. We need this thing to be 100. Okay, so what does n have to be for this sum to become roughly 100? Then so then we solve for n. N will have to be e to the power 100, of course. That would be the answer. Now, the reason I assign you to do this homework is it has an interesting feature to look at, that it will take e to the power 100 for the harmonic series to make it to 100. And you're thinking, well, so what? But that matters more than you think. Now, in the book says that they have a calculator, right? And I mean, they're using the computer to do the addition, and the computer is able to do 1 million additions per second, okay? Now, at that rate, if you were to do 1 million additions per second, how many seconds is that? Now, I did the math, and you can, of course, feel free to do it. As I did the math, is that this number is roughly 2.7 times 10 to the power 43. And what that means is if you do various math, I guess, I end up being, that equals to 8.5 times 10 to the 29 years. Seriously, it'll take 8 with 29 zeros following. That is, what kind of time frame are we talking about? And that is a lot longer past I think the Earth is going to exist, okay? Because the Earth is supposed to be good for another, what, 5 billion years or something? And so it's going to be long past humanity's existence, and might even be long past our galaxy can exist. So, and that means the harmonic series only made it to the first 100. The next 100 will come much slower. You see, it'll take much longer, the next 100. So the harmonic series, this is just an interesting tidbit. That is that while the harmonic series is diverging, that is increasing unto infinity, is taking its time. It's going to crawl up there very, very, very slowly. See? And and that should be something that is interesting to bear in mind. And with that, it marks the end of our section.